Hi guys, welcome back. So can you guess what we're gonna do today? That's right. So we're gonna go ahead and add and subtract radical expressions. So we're gonna open it up with this thing right here, like square roots. What are like square roots? So like square roots kind of sounds like terms, okay? But like square roots is pretty much square roots that have the same radicand. So in general, like radicals are radical terms that have the same radical part. Okay, so in this case 2 root 3 and negative 7 root 3, they're like square roots. Why? They're like square roots because they have the same radical part, so we can combine them if need be. 2 root 3 and negative 7 root 3, they are like terms. Why are they like terms? They are like terms because they're both numbers. So with the calculator, we could add them up and give a decimal approximation. Okay, so although they're like terms, they're not like radicals or they're not like square roots. Why not? Because they don't have the same radical part. Like this has a root 3 and this one does not. Okay, so the directions read add or subtract to simplify the expression. And then my favorite disclaimer when it comes to variables and radicals: assume all variables represent positive real numbers. And if we have that disclaimer, we don't have to worry about tossing in like an absolute value when need be. Okay, so now the question is, well, how do we let's go ahead and do a bonus problem. So let's just say that I asked you quick, simplify. We have negative 2x plus 6x. Okay, the first thing I would need to ask myself is this: are these terms like terms? I'm like, I don't know. Do they have the same variable part? Okay, they sure do. How do we combine them? Oh, cool. We add or subtract the coefficients and then tag along the variable part. Sum of negative 2 and 6 will give us 4, and then we'll tag along the variable part. And I kid you not, if you can do this bonus problem, you can do any problem in this unit. Of course, there's going to be radicals involved, so sometimes we have to do some steps in between. But the thing is, that's pretty much how it goes. So for problem A, we have negative 2 times the cube root of 5 plus 6 times the cube root of 5. So I'm going to ask myself, are these like radicals? I'm like, I don't know. Do they have the same radical part? Well, they sure do. Okay, so how are we going to combine them? I say coefficients in quotation marks, but I'm not going to show my face, okay? But like, what does it say? Air quotes, okay? They're not, negative 2 and 6 are not coefficients, because a coefficient is code for a number in front of the variable, and cube root of 5 is not a variable, but that's just how we speak. Okay, so we're going to combine the numbers before the radical part, namely negative 2 and 6. Negative 2 plus 6 will give us 4, and then we'll tag along the radical part. Okay, kind of like if we had a variable, we would tag along the variable part. Okay, all right, so we're gonna do a total of 7 problems. We just did 1, so let's go ahead and do 6 more. Okay, problem B, we have where am I? 3y square root of 2x minus 7y times the square root of 2x plus xy times the square root of 2x. Okay, fantastic. So what are the directions? The directions are add or subtract to simplify the expression. So if you have addition, add, subtraction, subtract. Okay, so I want to point out that the following. Yes, we do have radicals, but we also have variables outside the radical. So when we combine like terms, or we combine like radicals, not only are we gonna check to see if they have the same radical part, we gotta check to see if they have the entire variable slash radical part. So the first term has a y times the square root of 2x. The second term has a y times the square root of 2x, and I really can't do a third term, so we're just gonna focus on the 2 terms. Okay, so the first 2 terms have a y square root of 2x, so they're like terms. Let's combine them. Okay, when we combine the coefficients, 3 minus 7 will give us negative 4. And then we're going to tag along that cluster part, okay, times y times the square root of 2x. I changed the problem, sorry. I should start the video again, right? But who has time for that? Let's go ahead and bring down the rest of the problem. Plus xy times the square root of x. Cool, so let's see if we can keep combining. In this case, they both have the square root of 2x, but they don't have the same exact variable part. Like this has a y and this has a y and then some. So these are no longer like terms. If they were like terms, they will both need the same variable part times the same radical part. So they will both need an xy square root of 2x, and this one does not have xy square root of 2x. I will normally box this, but due to my technical difficulty, I need to write it over. So we have negative 4y times the square root of 2x plus xy times the square root of 2x. Okay, that is the answer, and we're sticking to it. Okay, I'm going to give you the book answer. Okay, is it a better answer? No, but again, you check your answers against the back of the book. So the directions read add or subtract to simplify the expression. Okay, we have established why we cannot add. Okay, they're not like terms. But the book said, I don't care if you can't add. So for some weird reason, we notice that both terms have a common factor. So for fake extra credit, let's go ahead factor it out. So in this case, the terms have a common factor of y, and the terms have a common factor of the square root of 2x. And then we are going to show the world what we're left with when we factor from the expression. First term over common factor, the y's cancel, the radicals cancel, and that will leave us with negative 4. Second term divided by the common factor, the y's cancel, the radicals cancel, and that will leave us with x. Okay, I really don't recommend you write it the way the book does. Why not? Yeah, I'm not fighting with the book, okay? The reason why is because it goes against everything that I tell the students. Students like to factor, okay? Like to factor even when they don't want to, okay? They like to do that effort, okay? So I like to tell students you only factor if it says factor or factor completely. For this problem, there is no reference to factor completely. The directions are just add or subtract. We added or subtracted until we couldn't anymore, so I would recommend you leave it as such. When you look at the answer in the back of the book, again, if you're an overachiever, you can factor for fake extra credit. I wouldn't, because we're not factoring, okay? But when you check the book answer, just distribute, and then you'll confirm that that's the same answer as you got. Okay, so that's the last time I'm going to make a big fuss about the book answer. Okay, so 7 problems. Where are we now? Problem number 3. Okay, problem C. So we have 5 times the square root of 12 times y to the 6 plus 6 times the square root of 75 times y to the 6. So for starters, these terms are not like terms because they don't have the same radical part, or in this case the same square root part. But I'm not going to just stop right there, because although they're not like terms, unlike the previous problem, the radicals are not simplified. Like I could simplify the square root of 12 times y to the 6. So let's do this. So because the index is 2, it would be nice if we can identify a perfect square factor. And in this case we can, namely 4. So we're going to use the we're going to use the product rule for radicals. So we have 5, 12. A nice way to write it will be 4 times 3. Okay, but I meant to say square root of 4 times square root of 3, and then we'll tag along the y to the 3, okay, to the factor that's not a perfect square. What about the rest of the problem? I don't have time for that, okay? So what I recommend is, like, you kind of see this like two pieces of the puzzle. Puzzle number 1. Look at the first term, simplify. When you're done, look at the rest of the puzzle. Puzzle number 2, piece 2, simplify, and then at the end add if possible. Okay, so let's look at the first half. So that will leave us with 5 times the square root of 4. Square root of 4 is 2 times the square root of 3, which we cannot simplify, times the square root of y to the 6. Okay, so let me go ahead and bust out a thinking area. Okay, square root of y to the 6. Okay, when we put that in exponential form, that will leave, or write it without the radical, that will leave us with y raised to the 6 over whatever the index is. 6 over 2. 6 divided by 2 will give us 3. So we will tell the world square root of y to the 6 gives us y cubed. But if you're like, I could just do this in my head, then go for it. You're like, oh yeah, square root of y to the 6. Oh, 2 goes into 6 3 times. Okay, then take out those 3 factors of y. Let's go ahead, clean up these factors outside the radical. Product of y cubed 5 and 2 will give us 10y cubed, and that is being multiplied by the square root of 3. Okay, so half the puzzle done, half more to go. So let's simplify the square root of 75 times y to the 6 however you can. So if we can think of a perfect square factor for 75, cool, and if we can't, then we don't. Okay, but I think if we think money, let's think quarters, 25. So we're going to rewrite square root of 75 as the square root of 25 times the square root of 3, and let's tag along those variables to the 3. Okay, something that I want to point out is this: when I simplify like the individual radicals, I'm not too concerned with my steps lining up because that slows me down. Okay, I don't even like look at this part. Okay, I just go to attack mode, and if the steps line up, cool, and if they don't, that's okay. Okay, let's go ahead, simplify what we can. The square root of 25 will give us 5, and that is being multiplied by the square root of 3, which will stay as square root of 3, times the square root of y squared. So the square root of y squared, what that boils down to is how many times does the index of 2 go into the exponent of 6. So once again, 2 goes into 6 exactly 3 times. If you don't want to do it in exponential form, something that I just do, sometimes I'll just do like the into symbol, okay, the division. How many times does the index go into the exponent? I'm like, oh yeah, it goes in 3 times. So this is why 3 factors of y come outside. Let's clean it up. Product of y squared 6 and 5 will give us 30y squared. And then we'll bring down the radical part. So I think for some miracle, by some miracle, my steps line up. They typically never do. Okay, so I'm going to show you what I do when my steps don't line up. We're going to have a visual break, and then at this point, we'll line up our results. Okay, so we have 10y cubed times the square root of 3. Now at this point, we will bring down the operation, which is plus. Okay, if I was lining up my steps, if that was my aim, then of course I would bring down the plus sign at each step. But again, that slows me down. Okay, plus the second part of this puzzle, 30y squared times the square root of 3. Cool. So in the beginning, we had said that the terms were not like radicals, or they were not like square roots, because they didn't have the square root, the same square root part. But we didn't box just the question itself, because although we couldn't add right now, the radicals, neither one was simplified. We simplified each one, and then look at this. Oh, what a beautiful gift. They were not like terms to begin with, but they are now. Okay, so let's go ahead and add. The sum of 10 and 30 will give us 40. And then we tag along that cluster part. Oh no, they're not like terms. Why not? Oh, because I don't know how to write. Okay, so square root of y to the 6, 2 goes into 6 3 times. We wrote 3, right? It would be nice if I wrote what I said. So let's go ahead and fix these. I know you caught it, but we're not live, so yeah, sorry about that. But the good thing is that I caught it before this video was actually uploaded. Okay, so we tag, so we had the 10 and 30 to make 40, and then we tag along that cluster part. Okay, if you ask someone what is that cluster part, no one will understand you. That's just words that we made up. Okay, so that variable radical part. Cool. So okay, so we're doing 7 problems. Where are we? I think that's our 3rd one. Let me go ahead hunt my 4th one. Okay, so the 4th problem has been located, so let's go ahead and do this. So we are asked to add and subtract to simplify the expression. These don't have the same exact radical part, so they're not like radicals, so we cannot subtract right now. But who knows, after we simplify the radicals, they may end up being like radicals, or they may not be. Who knows? It's a surprise. Let's do this. So let's simplify the first part. Cube root of x to the fourth y to the 7. Okay, if you want to do it in your head, go for it. I think I'm just going to do the division. Okay, for the cube root of x to the fourth, what that boils down to is this: how many times does the index go into that exponent? Okay, 3 goes into 4 at most once, with the remainder 1. So check it out. Since the quotient is 1, that means that one factor of x is going to come outside. Since the remainder is 1, that means that one factor of x will stay inside the radical. Okay, cube root of y to the 7. Okay, what that boils down to is how many times does the index go into the exponent? Okay, 3 goes into 7 at most 2 times, with the remainder 1. So let's do this. The quotient is 2, so that means that 2 factors of y are going to come outside. Okay, the remainder is 1. That means that one factor of y will stay in. Okay, so that's like what it simplifies to. Most of the time, I'm not too concerned with the variable factors being in alphabetical order, but because I want to see if I can ultimately add or subtract, it would be nice if things looked exactly the same, not kind of the same. So now let's go ahead and put them in alphabetical order. So x, y, z. Hold the z. Okay. That way we don't get nervous. Okay, and if you don't like the division, then go ahead, do the full-blown exponential form. Okay, keep the base, write the exponent as a fraction, and then highlight the I don't like to use more than one equal sign, sorry. That's one of my pet peeves. Okay, so quotient is 1, so that means that one factor of x will come outside. Remainder is 1, so that means that one factor of x will stay inside. You do what you need to do. Okay, let's go ahead, move on. Cube root of 64xy. Again, I'm not going to be too concerned with the steps lining up. I believe 64 is the perfect cube. So 1 to the third, 2 to the third, 3 to the third, 4 to the third. Yeah, it is a perfect cube. Okay, so cube root of 64, with your permission, we're just going to go straight to 4. If you're like, oh, I didn't see that, then write 64 as a product of prime factors and then make your groups of 3. Okay, cube root of x, we cannot simplify it. We need at least 3 x's to be simplified, so it will stay inside the radical. Cube root of y, same speech, so it will stay inside the radical. So my final results are not lined up, so let's go ahead to a visual break and line them up. So the first part of the puzzle simplified to xy squared times the cube root of xy. Let's go ahead, bring down the operation. Where am I? Which is minus the second part of this puzzle, which is 4 times the cube root of xy. So then I'm going to ask myself, are these like terms? Yes, no, maybe so. So the first term has the xy squared cube root of xy, and the second term does not. Okay, it does not suffice for both of these terms to have the same radical part. If we have variables outside the radical, then both of them need to have. So for me, these are not like terms, so there's no way that we can add or subtract. But again, let's go with the book answer. Not let go with the, let's touch base on the book answer, so that way you don't have a moment. So for some weird reason, your book says, I'm putting words in their mouth. That's just how I speak, okay? I have no idea what the book says, but I'm trying to justify like their answer, okay? So the book says, you know what? Yeah, we cannot add or subtract, but for fake extra credit, let's take out a common factor. Both terms have a common factor of cube root xy, so let's go ahead, factor it out. Would I recommend you do that? No, okay, but if you want to, then that's fine. When you factor it out, first term over common factor, that will leave you with xy squared. Second term over common factor, that will leave you with minus 4. Fantastic. So which answer do I want to see? You know what I want to see? Whichever one makes you happy. Of course, I will recommend with the top one, because the point of these exercises is to add or subtract, and we couldn't subtract at this point. Alright, so we got 4 problems, we need 3 more, and we're out. Problem E. Problem E, we have -2 times the 4th root of 32 minus 7 times the 4th root of 162. Fantastic. Okay, so let's do this. So first things first, are these terms like terms? So it sounds like a trick question. They are like terms because they're both numbers. Like there's no variables attached. They're both numbers. So with the calculator, we can combine with the calculator, not by hand. But now what I'm going to ask myself is this: are they like radicals? So do they have the same radical part? And the answer is no. So the question is, can I subtract right now? Like no. Okay, maybe like later. Okay, but right now, no. But the thing is, we can't just say like can't do it, because although they're not like radicals, we can simplify each radical. It would be nice for the 4th root of 32 if I can think of a factor that's a power of 4, but I have no time for that. So I'm going to bust out a thinking area, and we're going to rewrite 32 as a product of prime factors. So with your permission, I'm just going to fly through this because I know that you can do it on your own. Okay, so pause and rewind as many times need be. Okay, so 32 is the same as 2 to the 5th power. Okay, so we have -2 times the 4th root of, and I've given you my reason why throughout the series why I don't use exponents for repeated factors. So we have 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5. Okay, let's go ahead, focus on the first part of the puzzle before we can do the second piece. Since the index is 4, I want to make groups of 4, and everyone needs to wear that same suit. Okay, so we have 1, 2, 3, 4, and then we got a solo rider. Okay, so that will leave us with -2 times the 4th root of 2, 2, 2, 2. We have 4 factors of 2. Again, I recommend now that you use exponents for repeated factors, because it will make it easier to evaluate the 4th root of 2 to the 4th versus the 4th root of 16. Okay, times, we're using the product rule for radicals to split the factors, times the solo rider. Okay, let's go ahead, evaluate that first radical. Index is 4, power is 4. They're the same, so they pretty much undo each other or cancel each other out, and that will leave us with the radicand of 2. But what's going on with it? It's being multiplied by -2, and it's also being multiplied by the 4th root of 2. Okay, let's clean up those integer factors. Product of -2 and 2 is a -4, and that is being multiplied by the 4th root of 2. Okay, so one puzzle down, one more to go. The second piece of this puzzle, we have 7. Someone said, what happened to the subtraction sign? Remember, for me, my priority is not to ensure that the steps line up, so for that reason, I don't bring down the operation. If I choose to bring down the operation, then I gotta make sure that all my steps line up, and that really slows me down. Okay, so what is a factor that is a power of 4 from 162? I have no idea, so we're just gonna prime factor it. 162 is out of my comfort zone, but I know it's even, so we know 2 is a factor. We punch it in, it'll be 2 and 81, and now I'm in my zone. So we prime factor the 81, namely 9 and 9, and then we branch it out, and that will give us 3 times 3. So we have that 162 is the same as 2 times 1, 2, 3, 4 times 3 to the 4th power. Okay, so we have 4th root of 2 times, and you can just write your 3 to the 4th right now, but I want to keep the solution consistent. Okay, so the index is 4, so it would be nice if we can make groups of 4, and everyone needs to wear the same suit. We're going to have a solo rider with the 2, but we can make a group of 4 with the 3s, okay? So the groups, they get its own radical, like its own house party or cabana, whatever I was saying, okay? So that will give us 4th root of 1, 2, 3, 4, 3 to the 4th power, times the 4th root of that solo rider. Okay, so we still have 4th root of 162, but we used the product rule for radicals. Okay, let's go ahead, continue, and evaluate what we can. Fourth root of 3 to the fourth, index is 4, power is 4. They pretty much undo each other or cancel each other out, and that will leave you with the radicand of 3. What's the operation between 7 and 3? The operation is multiplication, okay, and that is being multiplied by the fourth root of 2. Okay, we're almost done. Take your time, multiply what you can. Product of 7 and 3 is 21, and that 21 is being multiplied by the fourth root of 2. Fantastic. So again, my priority when I add or subtract radical expressions is not necessarily to line up each step. Sometimes they do, sometimes they don't. So let's do a visual. Bring down our result along with the operation. So the first part of the puzzle, simplify to -4 times the fourth root of 2, and the operation is minus, and we're going to subtract from it 21 times the fourth root of 2. Okay, we had established in the beginning that the terms were not like radicals, so we couldn't subtract right now, but check it out, the terms are actually indeed like radicals. We just had to simplify in order to combine. So when we combine the numbers before the radical, namely -4 and -21, so that sum or difference, however you want to digest it, will give us -25, and then we tag along that common radical part. So the answer gives us -25 times the fourth root of 2. Okay, so that is our fifth problem. Let's go ahead, look for our sixth problem, and then we're almost out. Give me a sec. Alright, so our sixth and almost final problem has been located. So we have 2 times the radical plus 2 times the quotient of these radicals. So let's go ahead, simplify each puzzle, and then combine at the end or add if possible. So let's simplify this radical. Since the radicand is a fraction, we're going to use the quotient rule for radicals to split the top from the bottom. So we have square root of the numerator divided by the square root of the denominator. And now that we have a division problem, we can't just put a 2 in front. Now we're going to have to force the multiplication sign. Okay, so we have 2 times quotient of those radicals. So the square root of 36 will simplify to 6. That is nice. And while we're at it, why don't we cancel out the common factors? 2 and 6 have a common factor of 2. 2 goes into itself once and into 6 3 times. Okay, this is like a lot for me, so let me go ahead and write down what we have. So in the numerator, we have square root of 32. In the denominator, we have 3. Okay, let's go ahead, simplify. This problem, in an effort to have a cleaner solution to follow, we're going to simplify all the radicals in a thinking area. Okay, square root of 32, I almost want to say that we prime factored that one recently. Yeah, we did. Okay, look at your work. Okay, where am I? It's somewhere over there. So we have that 32 is the same as 2 to the 5th power. So let's go ahead and do that. Square root of 32 is the same as 2 times 2 times 2 times 2 times 2. Okay, if you lost your notes from like 10 minutes ago, then prime factor the 32 again. So let's go ahead, make our groups. Since the index is 2, hence the square root, we're going to make groups of 2, and everyone needs to wear the same suit. Okay, so we got a group of 2, we got a group of 2, and then we got a solo rider. Okay, so 2 times 2 will give us 4, or 2 squared. I really don't care how you do it. Okay, 2 times 2 gives us 4, or 2 squared, and then we got that solo rider. Now again, do you really have to prime factor the 4? No, for square roots, you know, if you're in your zone and you can think of perfect square factors, then go for it. We've done it in both ways. Okay, so square root of 2 squared, the square and the square root undo each other, and that will leave us with the radicand of 2. Square root of 2 squared, encore presentation. The square and the square root undo each other, and that will leave us with 2. The operation between the radical is multiplication, so why stop now? Okay, times the square root of 2. Product of the integer factors, namely 2 in itself, will give us 4, and that is being multiplied by the square root of 2. So let's go ahead bring that to our solution. Okay, so thanks to our hard work, we have that the square root of 32 simplifies to 4 root 2, and that's all over 3. Fantastic. So half the puzzle done. Now let's go ahead attack the second one. Okay, so on the right side, we have on the right side of the plus sign, we got 2 times this division problem. Now I want to point out that 27 and 108 do have common factors other than 1, but I don't feel so comfortable to cancel them out because they're not housed under the same radical. So we are going to use the quotient rule in reverse to write it under a single radical. So we're going to write this as square root of 27 over 108. Okay, and then what's going on with the quotient of radicals, now a single radical, we're multiplying it by 2. Because we no longer have a quotient of 2 radicals, the raised dot is no longer needed, but I did it for fake extra credit. Let's go ahead reduce this however we can. 27 and 108 I believe have a common factor of 9. Hopefully I know my 9's times tables. When we divide by 9, that will leave us with 3 over 12. But we can still keep reducing. Okay, 3 and 12 have a common factor of 3. When we reduce by 3, that will leave us with 1 over 4. I would rather work with 1 over 4 any day versus 27 and 108. Now, if you feel comfortable to evaluate the square root of 1/4, go for it, but I don't, so I'm going to show some work. We're going to go ahead and use the quotient rule for radicals to split the top from the bottom, but it's not necessary if you see it. I don't, and you're not going to take the test from me, so this is why I write a lot. Okay, so we used quotient rule for radicals to split the top from the bottom, and then what was going on with that radical? It was being multiplied by 2. Now I need the raised dot because we don't have 2 times 1 radical. We have 2 times a division problem. So let's simplify what we can. So we have 2 times the square root of 1 simplifies to 1. The square root of 4 simplifies to 2. And after all that work, what this boils down to is what is 2 times a half. Okay, quotient of 2 in itself will give us 1. And product of 1 in itself will give us 1. Okay, so that was a long journey. I need a visual break, a real break, but we gotta finish. Okay, the first part of the puzzle simplified to 4 square root of 2 over 3. The operation is plus, and the second part of the puzzle simplified to 1. Now the question is, can I combine these numbers by hand? You know, well, no, because one has a root 2 and the other one doesn't. But in this case, remember the directions. The directions read add or subtract to simplify the expression. So although the terms are not like radicals, we can add. Okay, so let's go ahead and add. We got a fraction. It's only one denominator, so that one denominator is the LCD. Let's take our time and write those equivalent fractions. So we need to make that denominator, let's write 1 as a fraction. Okay, we need to make that denominator of 1 look like a winner. And to make it a winner, let's go ahead and multiply top and bottom by 3. After we multiply top and bottom by 3, we will tell the world 1 is the same as 3 over 3. Okay. Thanks to our hard work, now that the denominators are the same, we have green light to proceed. So to add 2 fractions that have the same denominator, we're going to add the numerators and write the sum over the common denominator. We should call it a day, huh? Should we? Give me a sec. Alright, so by the looks of another letter, that means we have another problem. But the good news is that we have reached our 7th and final problem. Alright, let's do this. So at a first glance, are these bad boys? I should stop speaking like that, but I can't. At a first glance, are these radicals like radicals? No, they don't have the same radical part. Okay, but let's go ahead and simplify now, and then maybe we can subtract at the end. Okay, so first part of the puzzle, I have no idea what it simplifies to, so we're going to use the quotient rule for radicals to split the top from the bottom. Okay, so we're going to write this as square root of the numerator divided by square root of the denominator. Okay, so do what we gotta do. Okay, so let's take our time. I'm gonna focus my energy on that denominator. Square root of n to the fourth, what that boils down to is this: how many times does that index of 2 go into that exponent of 4? Okay, 2 goes into 4 exactly 2 times, so we're going to tell the world square root of n to the fourth simplifies to n squared. Fantastic. At this point, we're just going to focus our energy on simplifying the square root of 80. And you have ways to go about it. You can do the prime factor route, or you can think of perfect square factors. It's really a personal choice. I myself, when the numbers come to me, I prefer to think of a perfect square factor, but when they don't, then if they don't, they don't. So let's go ahead, write 80 as a product of prime factors, and then take it from there. Okay, so 80, where am I? One way to write it is 8 times 10. We branch out 80. I'm going to do 3 branches because I'm an overachiever. Okay, and then 10 is the same as 2 times 5. Okay, so thanks to our hard work, we have that the square root of 80, or 80, is the same as 2 times 2 times 2 times 2 times 5. Okay, that was too many 2's. Okay, 2 times 2 times 2, 4 of them, times 5. Okay, if you're not sure, just punch it in, punch in that product and confirm that you have 80. And that's all over the denominator in simplified form, which is n squared. Cool, so let's do this. Since the index is 2, we want to make groups of 2, and everyone needs to wear the same suit. So we got a group of 2, we got a group of 2, and then a solo rider. Whoever is in the group gets its own radical, and whoever's a solo rider, all those solo riders, they get tossed in a separate radical. Let me fix it so it looks like 5. So that will give us square root of 2 times 2, which is 2 squared. And again, you can write 4 because it's so much easier to evaluate square root of 4. But I'm giving you my reasons why I leave it in exponential form. With the exponent, sorry. Square root of 2 times 2. So square root of 2 squared, and then square root of 5. And that's all over n squared. Fantastic. So let's evaluate whatever square root that we can. So the first radical, the square and the square root undo each other, and that will leave us with 2. The square and the square root undo each other. Okay, and if you don't like what I say, then we say that exponent of 2, index of 2 undo each other. Same difference, and that will leave us with 2. The operations between the radicals is multiplication, so let's go ahead and insert our raised dot, and then we're multiplying that by a square root of 5. Cool. Let's bring down the rest of the puzzle. Oh, I'm so excited. We're almost done for the day. Product of the integer factors will give us 4, and that is being multiplied by the square root of 5, and that's all over n squared. Okay, so we got one piece down, one more piece to go. Remember, pause and rewind as many times as needed. Let's go ahead, look at the second piece. So square root of 81, I can't believe my eyes. I feel like crying. Okay, why? Because 81 is a perfect square. Okay, so that will make my life so much easier. Okay, square root of 81, that will give us 9. Square root of n to the 10th, again, what that boils down to is how many times does 2 go into the exponent of 10. Last time I checked, 2 goes into 10 exactly 5 times. So we're going to tell the world, since 2 goes into 10 exactly 5 times, and the square root of n to the 10th is just n to the 5 times, or n to the 5th, how normal people speak. So my results are not lined up, so we're definitely going to need that visual break. Okay, the first part of the puzzle simplified to 4 times the square root of 5 over n squared. The operation was minus, and the second part of the puzzle simplified to 9 over n to the 5th. Fantastic. Now, the directions read or read. Add or subtract to simplify the expression. We got two things separated by a minus sign, so guess what we're doing? We are subtracting, okay? So we have variables in the bottom, Lucky for us, it's the same variable, so to identify the LCD, we're going to multiply the different factors using the biggest exponent on each factor. In this case, it will be 5. Okay, so the LCD is n to the 5th. The first denominator, to make it look like a winner, we need to multiply it by 3 more factors of n. So let's do this. Multiply top and bottom by n cubed. Never forget to have your good notation. The second denominator is already a winner, so let's clean this up. Okay, product of n cubed 4 and the square root of 5 will give us 4 n cubed square root of 5, and that's all over n cubed times n squared. Well, that will give us n to the 5th. Bring down the rest of the problem, minus 9 over n to the 5th. Thanks to our hard work, the denominators are the same, so let's go ahead and proceed to subtract. Okay, to subtract two fractions that have the same denominator, we're going to subtract the numerators and write the difference over the common denominator. So we subtract the numerators, so 4 times n cubed times the square root of 5. Operation is minus. Subtract the numerators and then write the difference over the common denominator. Okay guys, so I said we were going to do 7 problems. We have reached our 7th and final problem. So we're out. Thanks.